All right, so continuing our look into how to differentiate more complex functions. Focus of this is what we call the product rule and the quotient rule. Basically, how you differentiate when you have a quotient of functions, as we see here, or a product. And so if I have one function being divided by the other, like I have my numerator and my denominator, in general, the quotient rule, if I want to find the derivative of this, I start with the derivative of the numerator. So the derivative of x cubed plus 7 is 3x squared, multiplied by the denominator as is, minus the other way around. The numerator as is, x cubed plus 7, times the derivative of the denominator, which in this case is still e to the power of x. So derivative of the numerator times the denominator minus the other way around. The numerator as is by the derivative of the denominator. And all of this good stuff is divided by the denominator squared. So e to the power of x squared. All right, and that said, while I've differentiated, I'll just clean this up a little bit. In my numerator, I can see I can take a factor of e to the power of x out of the numerator, which leaves me with 3x squared minus x cubed take away 7. When I take out that factor of e to the power of x, all divided by e to the power of x squared. And at this point, I have a factor of e to the power of x in the numerator and the denominator. Oh, wrong. There we go. And so a little bit simpler is just to write 3x squared minus x cubed take away 7 over e to the power of x. All right. So here, similar, exact same idea, except I have e to the power of negative x. Now I could use the quotient rule like before, or, because we always have options, e to the negative x. That is the same. If I rewrite this, I can write this as y equals x to the power of 3 plus 7 times e to the positive x, right? Dividing by a negative power, same as multiplying by a positive power. And if I do this, then I don't need to use the quotient rule. In fact, I'll use the product rule instead, which is a little bit cleaner. Anytime you have a product of two functions, the derivative is the derivative of, in this case, whatever comes first, although the order won't really matter. So the derivative of x cubed plus 7 is 3x squared times the second function left alone, plus the other way around. So x cubed plus 7 times the derivative of e to the power of x, which is the same thing. Now with the product rule, because when you have a product of functions, the order you multiply doesn't matter. Same thing here, we're adding, it doesn't really matter if I do this in a different order. I could do the derivative of this times this left alone plus the other way around. That said, like before, I have this factor of e to the power of x I can take out, so why not? Easy to do, take out a factor of e to the power of x. I have 3x squared plus x cubed plus 7. And I'm done. All right. So here, again, I want to use the quotient rule, my numerator, my denominator. So dy dx, my derivative of the numerator is 2x times the natural logarithm minus the other way around. So x squared plus 1 times the derivative of the ln of x, which is 1 of x. And all of this is divided by the ln of x all squared. All right, so kind of just showing you how I got these. That said, while I'm done, I don't really have to simplify it. As an HL student, we should be able to. And so in this case, I will write this. I'll do this in a few steps. I'll write this as 2x ln x minus, I'll write this as a single fraction, x squared plus 1 over x. Keep in mind, I'm just looking at the numerator here. If I want to put these together, I just find a common denominator. So multiply this by x and this by x. And as well, instead of showing all this being divided by the ln of x all squared, I can alternatively show this, because I don't want all these fractions inside fractions. Instead of dividing by ln of x all squared, I could multiply by 1 over the ln of x squared. All right, so now just to clean this up, if I look here, I have 2x squared, because I have an x times an x there to make my common denominator. So 2x squared times the ln of x minus x squared minus 1. Because again, I'm subtracting x squared and I'm subtracting 1. All of this is divided by x times the ln of x all squared. And so just to kind of clean this up a little bit, this is what I really had for my previous step. Oh, I got rid of the ln. There we go. And while we were done, like I was done at this step here, it is needlessly messy. And finding common denominators, writing complex fractions as a single fraction, these are all skills we should be familiar with in HL. Otherwise, our functions can get quickly out of hand and get needlessly messy for no reason. So last one, very similar. Let's get straight to it. So the derivative of my numerator, I'm going to use a chain rule. So first I have 3 times x squared plus 1 to the power of 2 times the derivative of the inside function, x squared plus 1. So that has a derivative of 2x. So everything you see here is the derivative of that using the chain rule. So that's a derivative of my numerator times the denominator times the ln of 2x minus the other way around, minus my numerator left alone times the derivative of my denominator, which again will require the chain rule. So the derivative of the ln of 2x is 1 over 2x times the derivative of 2x, which is 2. And all of this is being divided by the ln of 2x all squared. Okay, some quick things while I am done. Again, this is needlessly messy. If I look right here, I can definitely cancel those out. I have 1 over 2 multiplied by 2. I still have an x right here. So similarly, let me create a common denominator here. And I can, if I multiply the denominator by x and multiply the numerator by x, I have a common denominator. So let's focus on that, which means I have 3 times 2x times x. So that is 6x squared times the ln of 2x times x squared plus 1 squared minus, over here, all I have is x squared plus 1 all cubed. Keep in mind, all of this is over x. But as well, all of this is being divided by the ln of 2x all squared. So instead of having that double division, I will show this whole thing being multiplied by 1 over the ln of 2x all squared. And so putting it all together, I have almost the exact same thing as before. It's still quite messy, but not as crazy as it was at first. All right, so keep in mind again, I could, if I want to make this more messy or more work, if I look at my numerator, there is a common factor of x squared plus 1. I could take a couple of those out, but nothing cancels out, so I'm not going to bother doing that. And again, is still a complex function, but compared to what I started with back here, it's a lot simpler. All right. Just continuing, a bunch of examples. Again, I want to use what's the word I'm looking for? Quotient rule. I want to use the quotient rule here. So the derivative of e to the power of x is e to the power of x times cos x left as is, minus the other way around. E to the power of x times the derivative of cosine is minus sine. So I'm just going to write it as sine x and then change this to a plus because I'm multiplying by minus sign. And all of this divided by the denominator cos x all squared. If I look at my numerator, I could take out a factor of e to the power of x, but nothing cancels out, so I'm not going to. All right, similarly over here, I have e to the power of x to the power of 2, which means I have a quadratic function inside an exponential function, which means I'll have to use a chain rule at one point. So dy dx, the derivative of the numerator is the derivative of e to the power of x squared is e to the power of x squared times the derivative of x squared, which is 2x. And all that's times the denominator, all right? Minus e to the power of x squared times the derivative of the denominator, which again is minus sine x. So again, I'll just make that a plus and go divided by cos squared x. And like before, I could take out a common factor of e to the power of x squared, but like before, There's no clear things that make this much simpler, so I'll just leave it as it is. All right, sine x over ln x should be fairly quick. I don't have to use a chain rule here. The derivative of the numerator is cosine of x times ln x as is, minus other way around. Sine x times the derivative of ln x is 1 over x. So instead of writing it like this, since we use the derivative of ln x so much, I'll just go straight to showing this as sine x over x. And all of this is divided by the ln of x all squared. So like before, while I am done, we should be able to simplify this. And so instead of having these fractions inside fractions, let's find a common denominator. So I'll end up having x times the cos of x times the ln of x minus the sine of x. And all of this is over x, that's my numerator. However, I don't want to have another fraction below it, so I'm going to show, instead of this being divided, instead of dividing by ln x all squared, I'm going to think of it as everything here being multiplied by 1 over ln x all squared, which means in the end, my denominator is going to be x times the ln of x all squared. Now, looking at this carefully, maybe not be a bad idea to put some brackets around these, but nothing cancels out. I don't have any common factors in the numerator and the denominator, so I am just done. Lastly, same idea, just like a little bit of the chain rule I'll have to put in. And for some reason, my natural logarithm doesn't have an x. There you go. Now you have an x. And so the derivative of the numerator, so the derivative of sine is cosine of 5 minus 2x, but times the derivative of the inside function, which is negative 2. Right? So everything you see there is the derivative of just my numerator times the denominator times the ln of x minus the other way around. So sine of 5 minus 2x times 1 over x. Like before, I'll save myself a bit of time and just write it like this. And again, all of this over the ln of x all squared. And again, I'm essentially done. I'm just going to find a common denominator. It's very similar to the last one. Like multiply the top and bottom of this by x. And so in the end, my slightly simplified answer becomes negative 2x times the ln of x times the cosine of 5 minus 2x minus the sine of 5 minus 2x. And all this is over x times the natural logarithm of x squared. Ugh. All right, keep in mind, these things definitely require some practice. And if we never simplify our equations, when we have to start using them, we quite often just make mistakes because they're getting so out of hand. Although this is still a pretty complex function. All right, last question. A little bit different. I give you the derivative. Here's the function. Here's its derivative. There's just some constant c we need to figure out. I know it's an integer, which means its derivative should simplify quite nicely, and just what is the numerator of it. Several approaches. I'll do the most, standard approach. I'm just going to basically ignore this for the time being and differentiate this, so use the quotient rule. And so f prime of x, the derivative of x squared minus 4 is 2x times the denominator minus the other way around times the derivative of the denominator. So the denominator is the derivative of 2x plus 2. And all this is divided by x squared plus 2x all squared. All right, so that said, I know this must simplify a lot because I'm told the derivative is just some constant, some integer divided by x squared. So now it's no longer any calculus or derivatives works. It's simplification, it's polynomial work. So I'm going to distribute all this. When I do all that and the dust settles, it should end up with 2x squared plus 8x plus 8. That's when I combine all, so when I expand and simplify. The denominator, though, if you are, you may be tempted to multiply that all out. Keep in mind, it's not a bad idea inherently, but if I want to, I mean, I know it's going to simplify down to this, which means I know there's got to be some sort of factors that are going to cancel out. So I want to think about factors instead of just expanding. And so speaking of factors, if I look right here, there's a factor of x I can take out before I square it. So what you see highlighted in yellow, I can write as x times x plus 2. And all of that is squared. And in my numerator, I can take out a factor of 2. So my numerator, I'm taking out a factor of 2, so I get x squared plus 4x plus 4, which is a perfect square. In my denominator, I'm just going to write it as x squared times x plus 2 squared. And this right here is a perfect square. That is the same as x plus 2 all squared. And suddenly, I can see we're pretty much done. Because now I can see, hey, I have a factor of x plus 2 squared up here and down here. I can cancel those out. And so I can see my derivative, 2 over x squared, which means this ever so mysterious c must be 2. So I'll just finish it off and say, therefore, c equals 2. That's it. There's definitely other approaches. One thing that you may have noticed from the very start is that this is a difference of squares. And I mentioned already that you can take a factor of x out of here. You could actually simplify this pretty quickly almost right away, which will give us a much simpler function to differentiate. However, we are, like I've said, as HL students, we need to be proficient with fairly messy algebraic work because life is messy sometimes. We can't shy away from things being messy sometimes.